and hopefully it puts together several things. This is not very simple stuff. It takes a lot of picky, detailed reading and studying. What we see here is the typical axe potential, okay? It looks a little muted here compared to what we saw in skeletal muscle, but it's basically the same thing. We have time in milliseconds, and we see that an axe potential is let's say, initiated and over in about 4 milliseconds or less, okay? And then we see our millivolt range, -70 being typical resting membrane potential, and here we see about +30 as full depolarization, all right? So, let's see here. We have there's resting membrane potential. There we have sodium ion channel, okay? This one is voltage gated. This one is going to respond to changes in potential across the membrane. There is a potassium ion channel. It is also voltage gated, responds to changes in potential. Here we are at event number 1, resting state. Both of these gates are closed. We know that there are sodium leak channels, we know there are potassium leak channels, but the gates are closed. One thing we can see right off is that the sodium gate is a little different than the potassium gate. It has something called an activation gate and an inactivation gate. The next step, we see depolarization beginning, okay? And we see that the activation gate of the sodium ion channel opens and sodium rushes in. It comes in because there's a concentration gradient. There's a concentration difference, okay? We see that this is number 2, depolarization, and we see that number 2 is depicted right here on the graph, okay? The next step is we reach the peak, number 3, and the potassium ion gate, which was closed, has now been stimulated to open by potential changes right here, and the potassium ion gate opens, potassium rushes out of the cell. We see as the positive ion leaves the cell that the cell repolarizes. It goes back towards resting membrane potential. In number 4, we see an area that is known as hyperpolarization. The sodium ion gate closed as we got up into this area here. The potassium ion gate opened, but it is a slow opener and a slow closer. So it continues to let out excess potassium beyond the needs of resting membrane potential. And the cell becomes hyperpolarized. Okay? We can see that hyperpolarizing is not a huge difference, but it's probably -80, -85 millivolts. It is hyperpolarized. Okay? And then eventually, we'll see that these gates will both close and the sodium-potassium pump will put things back again. This is typical axe potential in a neuron. Okay? All right? This graph here tells us about permeability changes in the membrane of the cell. Maybe not something that you're going to go home and tell your friends about. Okay? But we do see how sodium ion permeability of the membrane changes dramatically as we get into number 2, and how potassium ion permeability changes dramatically as we get into step number 3, repolarization. Okay? Now, let me just double check to see if that's on here. Okay. Yeah, refraction comes later, so hold on. Okay. Do you have any questions? Anything you want to talk about at all? Anything at all? Take it step by step. We don't have to remember every single thing, but we want to know where the ions are moving, why they're moving, okay? What proteins are involved. All right? I'll leave you with this then, before we move on. This hyperpolarization affects the sensitivity of the neuron. So after a neuron has just gone through an axe potential, or as it's in axe potential, it may be totally insensitive to new stimuli. In this area right in here, it is less sensitive to new stimuli, but it will respond if the stimulus is strong enough. That's why we went through this whole thing of hyperpolarization, to let you know that the neuron is less sensitive while it is hyperpolarized. What does that mean? It means that if the stimulus is strong enough, the neuron will get right back into action potential if the stimulus is strong enough. Okay. All right. I figure you expect that.
Is that an essay question?
Is what an essay question?
Those steps.
Not yet. I will show you some questions at the break. Okay. You've heard about action potential in the neuron. Is there anything that you would like to discuss before we move on to something else? Yeah.
So does depolarization just focus on sodium and repolarization focus on potassium?
In a neuron, yes. Yep, that's how it's done. The massive flow of sodium into the cell, when the cell becomes more permeable to it, depolarizes. The massive flow of potassium outside of the cell repolarizes. Sodium-potassium pump puts everything back. Okay. Action potentials are no good if they do not move, if they do not propagate down an axon. The signal cannot be sent unless the action potential propagates down the axon. Okay? Sodium influx causes local currents. These local currents lead to depolarization in nearby membrane. The depolarization reaches threshold, voltage-gated ion channels open. Not knowing what it says back there, if this area of the membrane is in action potential, sodium ions are coming in here, the membrane over there is still connected, and the sodium moves in that direction because there's not much sodium over there. As it does, it begins to change the potential across the membrane, and then eventually voltage-gated ion channels open, more sodium rushes in, and it does it in the next place. So we go from action potential here, sodium rushing in, potassium leaving, to threshold reached here, sodium ion gates open, sodium rushes in, potassium leaves, sodium moves into this area, threshold is reached, voltage-gated ion channels open, sodium rushes in, potassium leaves, and it just propagates down the axon. Okay? So that's a lot of words. I hope that's all set up there. Okay? It's really that straightforward. This is trying to show you how it works. I think maybe, I don't know if I should tell you too much more. What this figure that comes from your book is simply showing is in this area here where the recording electrode is, the membrane is at rest, but there's an action potential nearby. And the arrows are showing the movement of positive ions into the cell. In this one here, we see that the ion movement has passed the electrode, and we went from resting membrane potential to a depolarized state. Okay? The electrode is staying in the same location. You go to the next one, and the ion concentrations, or the ion imbalance, has been restored at the electrode. Sodium continues to rush in downstream of the electrode because this area here is depolarizing. Sodium ion gates are opening as a result of that threshold depolarization. But back here, potassium left the cell and reestablished polarity across the membrane, and we see that the electrode is experiencing almost resting membrane potential again. Okay, so this is some example of propagation, all right? And where's the other one? Yeah, okay, all right? So we get a neuron to fire, and then we can send this signal anywhere in the body. It propagates. Seems like it might be a slow process. We see that moving past here doesn't take very much time at all, okay? All right. I'm not sure how much you need to be told that axe potentials are always the same magnitude. This is a slide that makes that clear once again. And it also reminds you that it's axe potential frequency that makes the difference. How fast they come, not a change in strength. Because they cannot change in strength. Low frequency axe potentials are just important as high frequency axe potentials in communication. Okay? A nice graphic depicting this pretty well. No action potential. Okay? There may be some graded potential occurring, but no action potential reached. And so we see voltage stimulus, we see no level of stimulus to the level of threshold. The central nervous system does not catch wind of this, whatever this signal happens to be. Graded potential may be occurring in here, but it's not enough to raise the threshold, so there is no voltage being carried by the neuron. Once we get to this point, though, where we start getting axe potentials, we now have an actual stimulus that is being turned into electrical signals that the brain or body parts can interpret. We can see here that as we go from this frequency of axe potentials to this frequency here, that the stimulus strength increases dramatically. And so it's just a graphic that reinforces what I've been telling you. Axe potential frequency is where we get a concept of strength of stimulus. Okay? Oh, I hesitate to tell you about this. This is in your book. There is a time where the neuron that has just gone through axe potential is completely insensitive to new stimuli, and there is a time where, shortly after a neuron has reached axe potential, where it is less likely to respond to stimulus. This area in green here is called the absolute refractory period. And it is from threshold until we get to right in here where we get into an area of depolarized or repolarizing neuron. What's going on here in absolute refraction is from here over, your sodium gates are open, so further neurotransmitter release by another neuron cannot open up any more gates, any more sodium gates. Can't be done. So you can be in this stage if you're a neuron, and I can hit you with a hammer and you just can't respond because you're already responding to the previous stimulus. Okay? In here, we have something called the sodium inactivation gate. You'll be home tonight reading about this. You say, yeah, I know what the heck he was talking about. Okay? There is something called the sodium inactivation gate, and it's really sillily complicated. And how the heck they ever figured out it was going on, I have no idea. The sodium ion channel in the axon opens upon depolarizing threshold depolarization. It stays open until we get to here, and then there's a little cork that sticks in it called an inactivation gate. And that cork sticks in it here, and the cork remains in place to here. No sodium goes through that gate when the cork is in place, the inactivation gate. It's right here that the sodium inactivation gate opens. And now the neuron is ready to be stimulated by neurotransmitter, but it's going to take more in order to get the neuron to reach axe potential. So in here then, in blue, or darker blue, we have something called the relative refractory period. And in the relative refractory period, it is not a cork in the sodium ion channel that's preventing any further sodium entry, okay? It's not because the ion channels are already open that the neuron is insensitive. It's because the neuron is hyperpolarized in the absolute